And last video, you recall, we were talking about exothermic and endothermic reactions. And I told you that the symbol that we use for expressing enthalpy is delta H. Remember that we have to use this delta to express a change in energy. We can't measure the enthalpy of something absolutely. We just measure it relative to something else. So we have to use this delta symbol, this triangle. So again, we have the term we use for enthalpy is sometimes called heat of a reaction. And again, it's just the amount of energy that's either consumed or released in an endothermic or exothermic reaction. One thing I didn't mention is that these reactions, for it to be truly known as enthalpy, these reactions have to occur at constant pressure. That's not an issue for us because in a laboratory, everything is really done at constant pressure in open beakers and open flasks and things like that. So that's why we can call the heat that we either put into a reaction or get out of a reaction, we can call that the enthalpy. Now the next term that I would like you to become familiar with sounds like enthalpy, but it's very different. And that's what I'm going to try to do in this video, is explain what entropy is, and then show you an equation, a very famous equation that links enthalpy and entropy into one universal equation. So these are from your notes. This is filled in, the lecture outline filled in, but so again, let's get back to what is entropy. So entropy is this delta S, and it's sometimes called disorder or randomness. So delta S is a measure of molecular disorder. It's the measure of the change in the disorder that accompanies a chemical change. It can be positive or negative, just like enthalpy can, but you have to look at it in a slightly different way. Whereas delta H being negative means that heat is released, a negative delta S means that there's actually a decrease in disorder. So a positive delta S would mean there's an increase in disorder. It can be a little bit confusing to understand that versus this. So one way we can explain entropy to you would be not through a chemical reaction, but through a physical process like ice melting. So solid water melting into liquid water is just a physical process. The water is still water, it's just changed its physical state. We say for that process that delta S is positive. It's going from a more ordered state to a less ordered state. So we say there's more disorder. The opposite process, where liquid water would freeze, becoming ice, would have a negative change in delta S. We say there's a decrease in disorder, or you could say an increase in order. So I know that's a little bit confusing, but I drew this little picture here to kind of give you an idea of what entropy is. There are many ways to look at entropy. The whole universe really obeys this fundamental law that the whole universe is getting more disordered as time goes on. Everything is sort of flying apart. Stars are getting farther from us. Things are breaking down as time progresses. But entropy, and a simple way to illustrate what entropy is would be, imagine this cube is a room. And let's say you release a volatile compound in one corner of the room, perfume, some sort of volatile solvent, gasoline, things like that. Well, eventually, within a minute or two, you're going to smell that chemical. So why does that happen? Well, what happens is entropy is causing that to happen. The compound wants to occupy the entire room. So the liquid will spontaneously evaporate into a gas. So we say that is an increase in disorder. So there's actually, this is a more ordered system, just having a little puddle of the volatile compound in a corner of a room as liquid. But it really will spontaneously or naturally evaporate into gas if it's volatile enough. So that would have a change in entropy delta S that's positive. So with time, what happens is this just eventually will fill the entire room with molecules of the volatile compound. And eventually this puddle will disappear, and you'll have just gas molecules all over the room, completely filling the room. That's what entropy is. This molecule wants to become more disordered. You can kind of think of it in your life as your house. Think of your apartment or your house. Your apartment or your house naturally gets messy as time progresses. Why is that? It's because, like this compound evaporating in this room, it's just more likely that your house is messy than in order. There's really only one way to have an ordered house. There's really only one way to have an ordered liquid here in the corner. The molecules are all together. Probability says that it's more likely that the molecules are all evaporated and filling the room. There's just an infinite number of ways that these molecules could occupy this room. Therefore, it's just much more probable that this situation is going to occur. Just like your house naturally gets messy as time progresses, it's just more likely to happen as time goes on. You have to put energy in to clean your house. How do we get this molecule to go back into a liquid form? Well, it would be much more difficult than cleaning your house, but we could do it, I guess, by cooling the room down so that this gas would condense back into a liquid. But it wouldn't necessarily go back into a little puddle in the corner. It would just sort of come back down as liquid. But the concept is still the same as cleaning your house. That's what entropy is. So getting back to our lecture outline here, again, just to quickly summarize, we have positive or negative enthalpy, exothermic, endothermic. We have positive entropy or negative entropy. So systems generally want to go in this direction, where you have an increase in entropy. Delta S is positive. So we have an equation that combines the enthalpy, the heat of a reaction, and the entropy. And it looks like this. It looks pretty simple, but it has this temperature variable in it, so it depends on temperature as well. So this is a very famous equation. It's named after a scientist named Gibbs, and so they gave it his initial G. And this symbol here is called free energy. And free energy, in the simplest sense of the word, is the amount of energy in a system that's available to do work after the heat of the process or reaction is taken place, or the heat flow, I should say, and the entropy of the molecules have either increased or decreased. And the free energy does depend on temperature. So I'm going to show you in this video how you can use this equation to predict or understand why some reactions or processes are spontaneous and why some are not. So what does spontaneous mean again? Well, in a numerical sense, if delta G is less than 0, is negative, the reaction is spontaneous. You can think of that like an exothermic reaction. Remember in the last video I showed you that exothermic means you have reactants at a high energy, products at a low energy, so energy is flowing high to low. Well, free energy can be looked at the same way. If the free energy of the reactants is higher than the free energy of the products, then you have what's called a spontaneous process. The word spontaneous means that process or reaction will naturally occur once you kickstart it. Once you give it enough activation energy, it will just keep going until one of the reactants runs out. Some examples of spontaneous processes or reactions are burning wood, fireworks, nuclear decay, like the decay of uranium fuel in nuclear reactors. It takes billions of years for that to decay to a safe level. Well, maybe not that long, but it takes many, many years to decay to a level where it won't harm humans. That's why they have to store nuclear fuel in caves and things like that away from people, so it won't harm the general public. So how do we do that? What do we do with that Gibbs free energy equation? Here it is again. So the enthalpy and entropy determine, 1, the amount of energy available to do work, and 2, if the reaction is spontaneous or not. So you really have 4 cases that are possible with this equation. You can have a situation in which you have an exothermic reaction. So you might have to pause this video and kind of think about each of these cases. But I'm just going to run through it rather quickly. So if you have an exothermic reaction, we generally say that's favorable. Reactions want to be exothermic, but not always. Or you have an endothermic reaction where heat must be put into the system for the reaction to go. Or you have, and also for entropy, you have it can either be positive, which is generally a favorable thing for reactions to follow. They want to be going in a direction that's ordered to disordered because, as I said, it's just more probable for that to occur. Or you have a negative change in delta S, which generally is not favorable, which is a decrease in disorder. So how do we apply those 4 cases? How do we get 4 different cases for what can happen in reactions? Well, you use this equation. You just think of it from a mathematical sense. If delta H is negative and you have a positive value here, just look at the numbers, how they would work. You'd have a negative number here and a positive value here. One thing is important to remember is temperature is always positive. T is a positive number. It goes from 0 to infinity. It's called the Kelvin scale. Room temperature is about 20 degrees Celsius. So on the Kelvin scale, that would be about 293 Kelvin. They had to invent the Kelvin scale because we couldn't put negative temperatures into equations or we couldn't put 0 necessarily into an equation. It would cause some of them to not make any sense. So that's one thing you need to, it's a new unit I don't think we've talked about in this class, but the temperature in Kelvin is the temperature in degrees C plus 273.15. So this is the Kelvin temperature here. So going back to our equation, or our 4 cases, so let's say we have, if this number is negative and this number is positive, you can see that we have a negative number minus a positive number times a positive number. So this T delta S term will be a positive number. So if you take a negative number and subtract a positive number, it's like adding the opposite. So you're always going to get a negative number. So that's why in this case the reaction is always spontaneous when it's exothermic and the entropy change is favorable. Looking at this case, if this is endothermic, this is a positive number, and you subtract a term T delta S, where this is a positive number and delta S is positive, so this is always positive. A positive minus a positive may or may not be negative depending on the relationship between delta H and delta S. This is generally favorable at high temperature, where this term here is greater than this term here. So that would make delta G less than 0. An example of that would be liquid water evaporating into a gas. That will only occur spontaneously at high temperature. Going back to this first case, where reactions are always spontaneous, would be like if you threw in a alkali metal like potassium into water. It's an explosive reaction, and you would get potassium hydroxide and hydrogen gas. When reactions that form gases usually are going to be spontaneous, because forming gases from solid and liquid is a good thing from a chemical reaction sense. The reaction wants to go in that direction. It's favorable from an entropy standpoint. There's more disorder on the right side of the equation, on the product side. There's more disorder on this in this second case. There's more disorder here when liquid water evaporates. So that's why delta S is positive. But that's an endothermic process. You have to add in energy to make liquid water evaporate. You have to be at a very high temperature for that to happen, to boil water. The third case is when you have an exothermic reaction, but you have an unfavorable change in entropy. Delta S is negative. So that means that that would be spontaneous. Delta G would be negative at low temperature. What sort of process would be an example of that? Well, that would be the opposite of this, essentially, where liquid water would freeze. Liquid water freezing is an exothermic process. It gives off heat, but it's going from liquid to solid. So you have an unfavorable change in entropy. Water molecules want to stay far apart, so they want to stay in a liquid form relative to being in a solid form. That's why this process here, going from liquid to solid, has a negative change in entropy. But this will occur if this term here, this negative delta H up here, if this is negative, if that's greater than this term is positive, you'll still have this number, this delta G, be negative. And it'll be spontaneous at low temperature. The fourth case is reactions that are never spontaneous. You can think of the photosynthesis reaction as being this case. It is an endothermic process because you have to add in energy to these molecules, the CO2 and water, to make them react to give you glucose and oxygen. And that's an input of energy, so you need sunlight for that to happen. That's why delta H is positive. And also, it's an unfavorable change in entropy. You're taking a very chaotic reactant system, so to speak, 12 molecules here, and making one large molecule and releasing oxygen gas. So if there's more molecules of gas on the left than there are on the right, that is an unfavorable change in entropy. Entropy is negative. So if you look at the Gibbs free energy equation, you'll see that if you plug in a positive number here and subtract from it a term here that's going to be, let's see, negative times, it's going to be negative, so subtracting a negative is always positive. You have a positive number plus a positive number, delta G will be always positive. Remember, in these four cases, we want delta G to be negative for it to be a spontaneous process. Again, a spontaneous process is one that naturally occurs. So a real-world example of a spontaneous process would be a ball rolling down a hill. It naturally occurs. You'll never see a ball roll up a hill unless you kick it. So, or water flowing over a dam from high altitude to low altitude. That's a spontaneous process. That will occur naturally. But water going in the opposite direction would need a pump, would need an input of energy. So that is not a spontaneous process. So I hope that was not too confusing. You might have to go back and listen to that again to fully understand these four cases. And we will finish up the thermodynamics topic in the next video.